Hello, physical science class. This is the 18D section of notes on metallic bonds. Metallic bonds tend to be between metals only. I want to think of, and your book describes here, the reason for metallic bonding being different. It is this: there is a whole sea of free electrons, right? A whole bunch of electrons out there. And when we think of metals, they're going to be, those electrons are going to be constantly moving and sharing with each other. Metallic bonds with positive metal ions are arranged in a crystal lattice immersed in a sea of negative electrons. So when we think of metals, they're bendable, they're stretchable, they can be hammered, right? All due to the fact that those electrons are involved in that sea kind of a concept. Valence electrons are free to roam the entire lattice structure. This achieves chemical stability without directly satisfying the octet rule, right? All those electrons are there, they're moving, and they're allowing for a sharing, to fill that octet, but they're not necessarily physically always in one place. You cannot use an electron dot notation to show this, because electron dot notation would show the presence or the location of each individual electron. Alloys are combinations of metals, right? If you melt down gold and you melt down silver and you mix them together, that's going to make an alloy, right? Metallic lattice. For identical spherical objects, most efficient arrangement would be a hexagon, closely packed, so HCP. Alloys are true compounds, alloys containing a mixture of microcrystals. Okay, I want to just reiterate some of the things I was saying there about metals. Because of that sea of electron concept, you get some properties, some ways that metals behave that other things don't. One of those words is malleable. Think of a mallet. You can pound something with a mallet. It's like a hammer, right? So metals can be dented, and yet they don't break. They can be ductile. Ductile means you're stretching. Maybe think of ducts. Ducts, like heat ducts or something like that, right? They're ductile, they're stretchable. They conduct electricity well. They conduct heat well, and they're shiny. Those kind of things we don't see with either of the other covalent or ionic bonds. Although we cannot see bonds between atoms, we can often predict the inner structure of an element or compound by observing its properties, right? When we look at a metal, for example, and we talked about it being malleable or stretchable or whatever, we can't see the inside of those atoms with our human eye, but we know that they behave the way they do because of their physical behaviors that we can see. But we have to know that that's traced back to their inner structure, which we can't see. And that helps us to kind of recognize how things behave together. Okay, that's all for this chapter and the 18D notes.